Okay, so today we're going to talk about repeated measure. So repeated measure is going to be different than the previous ANOVAs that we've talked about. So previous ANOVAs, one-way, two-way ANOVA, they're all between group designs. We focus on the between group differences and then between group sum of squares over within group sum of squares. That's the F value. So we wanted big between group differences against small within group differences, which would give us more likely a significant p-value. So that's been our focus for the past few weeks. And now we're going to get into repeated measure, which we're going to talk about within subject designs. So now we're not going to focus on between group differences. It's all going to be within each individual. So I'm going to give you some examples of why we do this and some conceptual understanding. So this is an experimental design. This is one of the most basic ones. So what we do is, let's say we're going to compare people who received CBT intervention over a control group. So let's say social anxiety. So we randomly assigned a group of social anxiety clients, half to a waitlist group, half to a CBT group. And then after they finish their CBT interventions, we take their social anxiety score. We assess them on social anxiety. And so we have their observations on their social anxiety scores. And then we do a comparison, see who has higher social anxiety after the treatment. So based on this, what kind of analysis would we use? One-way ANOVA. Yeah, so it's it's a simple one-way ANOVA. Let's compare these two groups, and they're different people. Okay, so if we find that people who receive therapy has lower social anxiety scores than people who were on the wait list, can we be 100% sure that the intervention works? Not 100. What kind of factors might be involved?
The two groups were different.
Yeah, they might be different to start with. Somehow the group that got therapy just had lower social anxiety. Mm-hmm. And that's what happened to one of my studies in the past. So here we don't know which group started like what. So that means that there are group differences between those assigned to the treatment group and assigned to control group. So if you wanted to control for that, want to take out that factor, what would we do? Okay, maybe this is not a good example. Let's say if we wanted to test CBT and psychodynamic. Mm-hmm. Okay, and then we randomly assign, so we don't know, they have different characteristics. So if I said the first row CBT, the second row psychodynamic, maybe there are certain characteristics about 3 of you, the 4 of you, that might influence. So if we wanted to account for that, control for that, what would be some options?
You mean control for differences among individuals?
Yes, that are assigned on to different groups.
Randomization.
This is randomization, but they're random. We don't know. They're, yeah.
Well, it's a lecture on repeated measures. So.
Yeah. So how it's related to repeated measures, right?
So would that be like you send, the first row to CBT first for a determined amount of time, and then they do a CBT for a second, or they do psychodynamic for a second part?
Exactly.
Okay.
So each person would do both. So now, so you're comparing CBT and psychodynamic. You would receive both treatments. And then, so when we're comparing, it takes out that individual difference because each person had CBT and each person had psychodynamic. Mary?
I'm just curious, because I've heard that if you go to therapy multiple times, sometimes you have validation rate by previous therapists.
Yes, so yeah, so this is the design that Kelly talked about, or that I was saying that, okay, you would get treatment 1 first, and then get treatment 2 second, but also there are issues with this design as well. It's not perfect, because getting CBT first versus getting psychodynamic second, or the opposite around, it would have an impact, because you might have some foundations, or you might be able to improve when you first receive therapy and reach a plateau, and then it's harder to improve after you've already improved. So there's almost that factor. So I think a better design for this would be, there's still 2 groups, but each person do receive the 2 different one, but just a different order. So that sort of accounts for that order effect. So so the thing is, if we're comparing treatment 1 and treatment 2, and if we use the same set of people, so the people characteristics will not be associated with the treatment modality, right? Because you're not going to be associated with CBT and you with psychodynamic. It's like all of you are going to get both CBT and psychodynamic. So it sort of controls for that between subjects, or like the individual characteristics factors. Does that make sense? Okay, so it's kind of abstractive, and I'll talk more about it. And I think it relates to some of the calculation, and then why repeated measure is different than one way ANOVA. So before, Michelle, did you have a question?
Yeah, I guess, no, it's fine.
Okay, so there's another type of design, which is we still randomly assign them to 2 groups, but then we have baseline scores. So we have pre and post. This is the design that I used in my perfectionism study. And so, but in here, we also have repeated measures. We measure people multiple times. So that's the essence of repeated measures. So this is some background about repeated measure, why we use it, but definitely it's not like this is a perfect design. I think there are still flaws and issues with all kinds of designs. So what is repeated measure? So the easiest way to say is that each case is measured more than once on the same dependent variable. And in other words, we often use this repeated measure is often used to track changes in the DV over time course of change, growth or decline. But I want you to know that it can also be used for other factors other than time. So it's not always, repeated measure doesn't always mean the same variable measured over time. There's other forms of repeated measure, which might not sound like repeated, but statistically it's similar because it has, the data points are not independent from each other. The data points or the scores are related to each other. Let me explain a little bit. So these are some examples, measured multiple times. So if we want to measure a person's relationship satisfaction premaritally, followed up 1 year immediately, immediately after their marriage, 1 year and 7 years. So this would be a repeated measure design. So we would have, each person would have 4 scores on relationship satisfaction across 4 different time points. So another one, which is not related to time, but it's also similar in terms of the stats, is from different non-independent perspectives. So what this means is that, okay, if we want to measure a couple's relationship satisfaction, and we ask both the wife and the husband, so we're asking 2 perspectives on the same thing, right? The same DV, their relationship satisfaction, and they share that relationship. So this is another form because there's shared variance there. So their scores are not independent of each other because they're in the same relationship. That's different from we ask different husbands about their own relationship satisfaction. That would be independent. My marriage satisfaction would be independent of Garrett's marriage satisfaction. So but my marital satisfaction is not independent of my wife's marital satisfaction. Does that make sense? So it's that shared variance that make repeated measure the analysis to use. And another example would be like in Olympics, like after going through gymnastics, there's judges giving out points, scores. And so those scores are all measure that individual's performance. And they're usually highly correlated. Like you don't see a 10 and a 2. Usually it's 10, 8, 9, or 3, 4, 5. So it's usually somewhat correlated so that it's not independent from each other. So when those are not independent from each other, that's when we use repeated measure analysis. So a third different example is, or a third different situation where we use independent repeated measure is when we use different measures repeatedly. Okay, so we use different measures. Like if you're going to assess someone's IQ, we use the Ways 4, and then we use the Stanford-Binet, and we use differential ability scale to assess the same person's IQ. And if you want to see if the IQ is different across these 3 different assessments, then we're doing a repeated measure ANOVA test. Does that make sense? Because there's shared variance. It's not independent from each other. So what are the advantages of using repeated measure or this kind of design? From a design perspective, it's more efficient. So like I said, if I was to compare psychodynamics and CBT, and I needed an N or sample size of 4, so I would just take 4 people and then have them do both. But if I was doing the one-way ANOVA, I would have to have 4 in each group. So it would double my need for sample size. So I would need to recruit more. And then I would also need to explain more about the procedure and stuff. But if I'm using the same participants, once they do it, they're trained, they know how to go through it. I don't need to go through informed consent and train them about the experiment again. So that's from an experimental design, more the practical, logical aspects. And from a statistical aspect, it's more powerful. So this is the phrase, participants serve as their own control. It's not something we say in daily life, but what I mean here is that sort of like what I described there, everyone's receiving both conditions. So the conditions applied are in the same setting, at least the participants. They're not applied to different groups of people. They're applied to the same set of people. And so that takes out some of the random factors involved. So differences associated with case themselves are assessed and subtracted from the error term. So when we were calculating the F value, we had this for one-way ANOVA between group variance. And then sum of squares, mean squares, divided by the mean squares of within group difference. So the larger the denominator, the smaller the F. Okay, so with this repeated measure, we take out the variance that's between subjects because each individual is their own control. It doesn't matter if you're different from each other. So we subtract that aspect from the denominator, which leads to a larger F. So I'll talk more about that when I talk about the sum of squares. But before we move there, I'm going to talk about 3 designs that we're going to discuss or introduce under this repeated measure unit. One is a one-way repeated measure design, which is like marital satisfaction over time. And a factorial repeated measure design is that we have more than one IVs. and all the IVs are measured over time. I'll give you examples when we get to that unit. And then there's a mixed design, and the mixed design is that there's two IVs, and one IV is a repeated measure IV, and then the other IV is between group IV. It's a randomized assignment between group IVs. So it's kind of like this design here. So here we have a between group design, so comparing treatment group versus control group, and then we also have a repeated measure variable that's measured over time. So this is a mixed design, and then this is a one-way repeated measure design where we measure across time, and we want to compare if there's difference over time. Make sense so far? Okay, so these are some characteristics about repeated measure. Variance of interest occurs within the participants. So within each of you, you've now received both CBT and psychodynamic. So that difference between CBT and psychodynamic is within each individual subject. It's not anymore across different groups. So each subject serves as his or her own control, and individual difference do not affect difference between the treatment group. Within group variance is no longer the error term. Now we have a smaller error, and which will lead to a larger F ratio. So this is the components of the sum of squares. So for repeated measure, sum of square total equals the sum of squares of the repeated measure IV, and then the sum of squares between subjects, and then the error term. So there's a sum of squares between subjects, which is new. And so this is how it looks like. So total sum of squares would be the sum of squares of the IV of interest, and then the sum of squares of the error. So this, like in one-way ANOVA, the F value would be this divided by this, like the mean square of this by this. And now, this is split into two parts. The random factors, some factors are between subjects, some error are within subjects. And because the between, the variable that we're interested in is measured over time, and so you are your own control, and then we don't need to account for this between subject error. I know that wasn't clear. I struggle myself. Okay, so now this is how degrees of freedom are calculated, and I think this would be important to know. So for the sum of squares for the IV, the IV over time, it would be the levels, like if it was measured across 4 time point, it would be 4 minus 1. So the degree of freedom would be 3. And then here is the sum of squares for the total error, which would be this. But in terms of the F value, we're going to only use this error. We're going to take out the sum of squares between subjects. And this would be A minus 1 times S is the number of subjects. A minus 1 times S minus 1. So this would be the degrees of freedom for the error. And then the total degrees of freedom would be N, total number of time points minus 1, or total number of data points minus 1. And data points would be how many participants times the time points that they are measured. So that would be the degrees of freedom there.